Assalamualaikum warahmatullahi wabarakatuh, and we meet again. Previously in the first video, we already see some highlights on the shear strength, different shear strength with the different materials, and some of the shear failure. Alright, so we know now soil is generally fail in shear, so we can have a failure surface, or in 3D it is a failure envelope, and in one time at the failure zone or failure line we can have a mobilized shear, actually due to the weight here inside of the top part of the soil, and outside usually it is a resisting force. What the important things for the shear failure plane is the soil grains that are involved in the area usually not crushing to each other, it just slide over to each other so when we have a higher groundwater table, the sliding process is much more easier to occur, so that's why it is danger if we have a very high groundwater level. And at the failure line, we can still measure the normal stress, and we can have a tau mobilized and also tau that resists the failure. So as I mentioned in previous video, that at the failure surface, the shear stress when reach the failure is reaching the shear strength, tau F. So what is tau F? Okay, it is come from the Moore-Coulomb equation. So in Moore-Coulomb frictional law usually have a few parameters. Okay. So first one, as we can see here, it is a cohesion parameter. So if we have a clayey type of soil, or silt, or sandy clay, and so on, as long as it has a cohesion, so it is having a parameter of C value. So C value usually in kilopascal or kilonewton per meter cube. And C value, of course, it is diverse from one soil type to another soil type. Second is the internal friction angle. Phi value. So note that in the soil particle, they have effective strength of themselves, but this strength also combine and producing internal friction, and a similar value of internal friction. So let's say like that. So the phi value is very important, especially when we designing a slope. Okay? Let's say we have an embankment. So note that beta of the embankment slope should be lesser than the internal friction angle of soil. This is a rule of thumb to ensure the slope is stable. If we would like to have a beta much more higher compared to internal friction angle of the soil properties, so we need to design some support mechanisms such as a gabion, okay, sheet wire, and so on, to ensure the slope stability. Alright, next, the component that also we have in the Moore-Coulomb is the normal stress. So just now we can have a failure line in the circular mode. Okay, failure line in the circular mode, failure line or failure envelope. So let's say we zoom one area here. So we have a failure line like this. So we can calculate the normal stress from here or here. So as long as we can know the gamma, what type of the soil, is it dry soil, so gamma dry, moist soil, so it is a gamma bulk, or it has water in it, so we need to calculate pore water pressure, so we can calculate the stress normal. So the stress normal can be either in the total condition, stress total, or in the effective condition. Effective condition. So I hope you still remember. Effective is stress normal minus the pore water pressure. Similarly, at the similar failure lines, so we can have a tau that resists and also that mobilize the failure. F, F. Alright, next let's see the factor that will control the shear strength. So it can be a soil composition. So we have a vast factor for the soil composition itself, the mineralogy, grain size distribution from the sieve results, shape of the particles, pore fluid type, iron, and pore fluid. Okay? Iron on grain or and in pore fluid. Next is the initial state of the soil. What the initial state work ratio? Is it effective normal stress or total normal stress? And what is the stress history? Okay, stress history, if you continue to learn in geotechnics 1 later on in second year. So stress history is a pressure P sub C, pre-consolidated pressure. Is it higher or similar to the current pressure? So it is affecting the shear strength. Similarly, the loose condition, dense condition, OCR, NC, stiff, soft, and so on, dilative, also can affect the shear strength. Structure, so structure, of course, almost similar to this one. And loading condition, is it effective? Is it drain? We allow water, we assume the ground allow water to move farther away, or undrained, we just assume the soil condition is not allowing any water to move out. And what is the rate, the dynamic, the time history, and so on. Okay, for these courses, we just assume a very simple condition. So let's see the Moore Coulomb failure criterion in terms of graph presentation. Okay, so when we have a soil, a ground that we would like to build any building in here, so usually we will do a bore log activity. We will make some well, take soil sample and put it outside. So bring to the lab and we can prepare a data. We can plot the tau and also stress normal of the soil. As long we know unit weight, C, Phi, and so on. So let's say this is results from the series of the soil sample. The soil sample is quite small, not big. Can comes in the 50 millimeter of the diameter, with a height about 50 millimeter also, or times 2. And from the tau and normal stress, normal graph, so we can define the cohesion and also the phi angle. And if we have any more Coulomb, let's say we know the condition at site, what is the minor principal stress and the major principal stress that acting to the soil condition there. Let's say if you want to have a house, we want to have a house, so we will know additional loading that it be included in the major principal stress. So we can plot a graph. let's say like this one, having the value of stress 3 and stress 1. So this curve is a more Coulomb curve, more Coulomb curve. And this is failure line. So failure line might be, let's say it is having a bigger building. So the failure line might here. So might occur like a circular failure line. So sample that taken at the failure line will touch the molecule from the sample that taken at the failure zone will touch the failure envelope. So at the failure envelope, okay, so at the failure envelope, we can read the shear strength at failure and also the normal stress at failure. And not to forget, we can, if we know the middle point of the mole circle, we can also know the 2 theta, the theta angle. Theta angle is another parameter in the mole coulomb. Okay. So in general, we need to remember this is the mole coulomb equation. Tau at F equal to cohesion plus the stress normal times the tangent of internal friction angle of soil. Okay. So C and phi are the measures of the shear strength. If we have higher value of C, higher value of phi, so the higher the shear strength will be. Alright, so we already see C just now, phi, how to get it from the graph. As I mentioned earlier, we can have a different condition of total shear strength or effective shear strength. So we can have a different parameter of C. So C for total is only C, P, but for effective we need to add the prime attribute, C prime, Phi prime. So this is general equation of mole coulomb, and just now I also mentioned what is stress 1 and stress 3. So cohesive is such as a clay and silk, but cohesionless soil only have a phi value where the C is 0. Similarly for cohesive, when we have a C value, so phi usually 0, especially for clay. Okay. But not to forget, we can also have another type of soil, actually the combination of two types. So let's say we have a clayey sand. So of course we will have C value and also phi value. Alright, so this is the definition of the cohesion sticking together of a likely material, and internal friction angle is stress dependent component that sliding to each other, right? And let's see the mole coulomb. Okay, yeah, I think this is similar as the previous slide. Okay, this one. So just now I mentioned that we can obtain theta from the mole coulomb curve. Okay, so let's say this is a result from a soil sample of a cylinder from a ground that that collected at the zone of failure, at the failure line. So that's why it's touching the failure envelope, right? So it has C and phi value. So if we want to know what the value from of the failure for the stress normal and also tau at failure, not only we can sketch the graph, but we can also actually calculate as long as we know the stress 1 and also the theta, stress 1, stress 3 and the theta value. So this is equation for the stress normal at failure and also tau failure. And note that theta is also can be defined as 45 degree times the plus the internal friction angle divided by 2. And similarly, we can relate the stress 1 to stress 3 by using this equation. So I think I stop here for now. So until we meet again in the next